So here we have question 6 from paper 1 2020, and we're talking about a rider going down a chute on a sled down towards the water, which must be rather fun. And we're told that we're going to use some light gates to try and work out how fast this rider is going at the bottom. We know if we're going to work out how fast, that's speed, so it's speed, as we know, is distance over time. So first thing to do is look through, are there some answers we can get rid of that have got nothing to do with distance or time? Well, that's gravitational field strength, mass of the rider, and temperature of the surroundings, which kind of leaves us with time for the sled to go past, yep, and length of the sled. Well, the length of the sled is the distance that is being moved in the time that the sled goes past. So yeah, that's the next answer. On to 6.2, and this question then, we are told that we have a decrease in gravitational potential energy of 8.33 kilojoules. The rider's going through 7 meters, and we know that gravitational field strength, 9.8. We've been asked to find the mass. Well, I'm sure you remember that GPE is mgh. That's probably a formula you're going to have to learn. And we're after the mass, so I would do the algebra first. So in order to get mass on its own, firstly, let's divide by little g, because it's timesing at the moment, so dividing it will get rid. So we divide both sides by small g, so we get the gravitational potential energy over small g equals m times h. And so the next step is simply just to divide by h to get the m on its own. So now we get GPE over GH equals m. So at last we've found a use for some of those maths lessons when you practice your algebra. Now it's just a question of putting in the numbers. So for the GPE, that was 8.33, but beware, this is a trap, it's kilojoules, so you have to multiply it by 1,000, because that's what the K means. So it's 8330. Now we're dividing it by 9.8 for G times the H of 17. When you put that jolly lot into your calculator, you get 50 kilograms, which is probably a good height for, I don't know, year 7 kid, year 6, that sort of age. So this is a good figure. You also know you're onto something because you've got a really nice answer out on your calculator. That's not got any decimal points or loads of significant figures, and that's always a clue that you're on the right line. It's not a guarantee, but it is a good clue. Moving on then, this is a really great question, and it says, at the bottom of the slide, all the riders have the same speed, approximately. Explain why. Well, in order to do this really, you have to jump into some algebra. So first of all, let's just remind ourselves what's happening. If you drop an object off a cliff, then at the top of that object, top of the cliff even, it's got no kinetic energy because it's not moving. But it does have a good stack of gravitational potential energy because it's quite high. Anyway, as the ball falls, so its gravitational potential energy turns into kinetic energy until at the fraction it actually kind of hits the floor there, it's now got no gravitational potential energy because its height is 0, which means that all the gravitational potential energy you had at the top has turned into kinetic energy at the bottom. And that's the key to this question. So first of all, we can say that GPE at the top equals EK, or kinetic energy, at the bottom. And of course, with all sorts of physics questions, we have to say, assuming something. And in this case, we're assuming that air resistance makes no difference. There's no energy loss, in other words. Given that assumption, let's go ahead and put in the formulas. So that'll be mgh for gravitational potential energy is a half mv squared for kinetic energy. Now we need to end up with a formula for the speed or velocity which says v equals. That's what we're after, so we need to do some algebra here. And of course, the first thing you should notice, oh joy, is that there's an m on each side, and so we can cancel those out, which leaves us with gh equals a half v squared. Now, in order to get v on its own, we need to multiply by 2 to get rid of the half. So that implies that 2gh equals v squared. So in other words, we can now take the square root of 2gh, and that will give us v. And there's our answer. So the velocity is equal to the square root of 2 times g times h, and you'll probably get 2 marks for that. So we've got to the point of saying that there is no mass in our equation. So let's see if we can put that into some sort of sentence then to describe why they all have the same speed. So let's go. All riders will be going at the same speed when they finish the ride. F-I-N-I-S-H-E, let's get rid of that E, because there is no mass in our equation. Therefore, mass makes no difference. Awesome. Who would have thought, eh? But why is it approximately? Why does it say up in the question up there that they have approximately the same speed? Well, this is because, in actual fact, you can't ignore air resistance, can you? That's cheating. Of course, air resistance is going to make a difference here. If you're a tall adult compared to a small child, the tall adult clearly is going to have a larger air resistance because they've got a bigger surface area, and they'll therefore lose more energy to the surroundings, and therefore not all of the GPE is going to get into kinetic energy, and so they won't go quite as fast. So let's put that into words. A tall person has a greater surface area than a short one, and so in reality a tall person will lose more of their GPE to friction, i.e. air resistance, and so their final speed will be less. And that's the end of a really great question.